Hi, everyone. Hope you're having a great Friday. Hope that all your transition to online classes has gone smoothly. So we're here today to finish up chapter 7 and start chapter 8. So what we have to finish in chapter 7 is we're going to talk about the reduction of alkynes. There's going to be 3 reactions there. And then we'll talk about something called organic synthesis. All right, after that, we'll go ahead and start chapter 8, which is going to introduce a new type of reactivity, and we'll be dealing with something called free radicals or just radicals. Okay, so let's go ahead and finish up chapter 7 first by talking about the reduction of alkynes. Okay, so as I mentioned, there's going to be 3 different reactions we're going to learn here. And we can think about our general, if we go back to chapter 6 and think about the reduction of alkenes, what we saw in that case was that, when we added H2 across the alkene, we got to the alkane. And so I want you to think about, the alkyne having 2 pi bonds. So there's basically, we could add 2 equivalents of H2 across the carbon-carbon double bond. And so if we added 2 equivalents, we'd get to the alkane. But if we added only 1 equivalent of H2, we would either get to the E or the Z alkene. Okay, and so we don't actually control these reactions by the amount of hydrogen that's added, but rather by the catalyst or the conditions. Okay, so let's introduce the 3 reactions that fall under the category of reduction of alkynes. So the first one we'll label A is catalytic reduction to alkanes. Okay, so the first one is going to be all the way to alkanes. Okay, and so for each of these, we're not going to talk about the mechanism, but I'm going to give you the general reaction, one example. Okay, so here's our alkyne, and it doesn't matter if it's internal or terminal. And the conditions here actually are the same as if we were reducing an alkene. So we're going to have H2 gas and then some catalyst, which could be palladium, platinum, or nickel. Okay, and so under these conditions, we would reduce both pi bonds of the alkyne, and so that would get us to the alkane. Okay, so we can notice, if you were to draw the structure then, notice how both carbons of the alkyne now have 2 hydrogens. So it's as if we were, adding 2 equivalents of hydrogen, but I should note here that we generally can't control the amount of hydrogen gas that we are utilizing in our reactions. And so typically H2 is always used in a great excess. And so as I mentioned, we'll control the way that H2 or the amount of H2 that adds by using different reagents. So when we use palladium, platinum, or nickel, we can fully reduce the alkyne all the way to the corresponding alkane. Okay, so alkane that was. So let's go ahead and look at an example. So let's look at this molecule. All right, so we're going to take this alkyne and we're going to react it with H2 gas, and then we'll use, it doesn't matter, palladium, platinum, or nickel. And so again, with these alkyne reactions, I'd strongly encourage you to number your carbons so that you don't lose track of any carbons when you're converting the alkyne to some other, functional group, specifically when you're changing the hybridization to sp2 or sp3. Okay, so it doesn't matter that this is, a terminal alkyne, we're still going to go ahead and correspond it or convert it to the corresponding alkane. And so we can see this 3-carbon chain alkane. And notice how we're not affecting benzene. That was true of all the reactions of alkenes, still true of the reactions of alkynes. Okay, so our next reaction that we'll label B, is going to be, again, a catalytic reduction. But this time we're going to change the catalyst that we're using, and that's going to allow us to stop at the Z alkene. Okay, so to a Z alkene. All right, so let's go ahead and look at our example here. Okay, so we're going to use H2 gas again, and we're not controlling the amount of H2, but we are going to use a different catalyst. And this catalyst is called Lindlar's catalyst. And I'll describe what that is here in just a second. But what we need to recognize is that when we have Lindlar's catalyst in place of, palladium, platinum, or nickel, we are able to stop as if we just added 1 equivalent of hydrogen. Okay, so we would get to the Z alkene. So notice that this alkene has Z geometry where the 2 R groups are on the same side of the alkene. Okay, so what is Lindlar's catalyst? Okay, so Lindlar's catalyst. All right, so Lindlar's catalyst is basically a poisoned version of palladium where we've basically doped the palladium with something that's attenuating its reactivity or affecting its reactivity. And so what we've doped that palladium with is calcium carbonate and lead, Pb. Okay, so Lindlar's catalyst is palladium, calcium carbonate, and lead. And this affects the reactivity of palladium and really allows us to only reduce the more reactive pi bond, the first pi bond of the alkyne. And then the alkenes are less susceptible to reduction, and so we're able to control the reduction to stop at the alkene. Okay, and since Lindlar's catalyst is operating in a similar manner to just palladium, platinum, or nickel, it still delivers both hydrogens from the same face. All right, so let's look at one example using Lindlar's catalyst. All right, so again, let's go ahead and number the carbons of our alkyne, and then we're going to do this reaction with H2. And you know how this is going to appear as it relates to reagents is most people just write Lindlar's here, which is fine. You could also see it as palladium, calcium carbonate, and lead. All right, so I'm going to go ahead and draw the alkene in its Z geometry first, and then we can fill in the other carbons. So that was carbons 1, 2, 3, and 4. So then we need carbons 5 and 6. So let's go ahead and count those carbons. All right, so notice how the alkyne was between carbon 2 and 3. The alkene is also between carbons 2 and 3. And notice how it's taking on this Z geometry. In other words, carbon 1 and carbon 4 are on the same side of the alkene, carbon-carbon double bond. All right, our last reaction of this chapter and our last reduction is actually doesn't use hydrogen as the reductant. We're gonna talk about a slightly different mode of reduction. And so this reduction is dissolving metal reduction. And that's gonna give us E alkenes. Okay, so let's look at our same generic example as a starting material, and then we're going to go ahead and use our conditions, which is sodium metal, so that's sodium 0. Okay, so that 0 is telling us that it's not the oxidized or reduced form of sodium. It's not sodium cation that you would see like in sodium chloride, but instead it's the pure metal Na0. Let me try to make that 0 a little bit more clear. All right, and then we're going to dissolve that in ammonia liquid. Okay, so this is why it's called dissolving metal, because we're going to dissolve our pure metal sodium in ammonia. All right, and the products of this reaction are going to be the E alkene. So notice how the two R groups are on opposite sides of our carbon-carbon double bond. If we were to cut our double bond in half, we can see R on one side and R prime or R1 on the other side. Okay, so a little bit about this mechanism, although we're not going to write it out in full, is so this reaction actually goes through free radicals, which we'll introduce in the next chapter. But both atoms or both bonds to the new hydrogens and the products aren't forming at the same time. And so we have this chance to equilibrate to the more stable alkene, which we've learned to be the E alkene or the trans alkene. Okay, so let's go ahead and look at one example of this reaction, and then we'll finish up this chapter by talking about synthesis. Okay, so let's look at that, and we're going to number the carbons of our carbon chain outside of benzene. Our conditions are sodium 0 and ammonia liquid. All right, so then in the products, we should have a 4-carbon chain. Our alkene should be between carbons 2 and 3. And so notice how we have formed an E alkene or a trans alkene. Okay, one last thing I want to mention is, how would you know if you're using sodium and ammonia in dissolving metal reduction, or if you wanted to use H2 and Lindlar? So that will depend on if you want the E or the Z alkene. But there is one case in which it doesn't matter which reduction you choose, in that dissolving metal reduction and H2 and Lindlar give us the same products. And that's if you were to have a terminal alkyne. So I just want to show one example of that to highlight that issue. Okay, so for example, if we took this 1-butyne and we reacted it under either conditions, okay, so we could take H2 and Lindlar, or we could take dissolving metal reduction with sodium 0 and ammonia. Okay, so since we have a terminal alkyne, we'll end up with a terminal alkene. And so notice how there is no geometry associated with that alkene because carbon 1 has 2 hydrogens bound to it. Okay, so when you're reducing a terminal alkyne to an alkene, it doesn't matter which reducing agent you use between the two H2 and Lindlar and sodium and ammonia, because there is no easy geometry of that corresponding product. Okay, and if you wanted to go to the 4-carbon chain alkane, then you would use H2 and palladium, platinum, or nickel. All right, so that finishes up the reaction section of this chapter. What we have left is to talk about something called organic synthesis, which isn't exactly any new reactions, but instead, okay, sorry about that quick pause. I had a little person requesting an apple, so I had to take care of that quick, but I'm back and ready to talk about organic synthesis. Okay, so as I was saying, organic synthesis is not necessarily, we're not gonna be learning any new reactions, but what we're gonna be talking about is, what do we actually do with all these reactions that we've been learning over the last couple of weeks in lecture? Okay, so if you thought about what an organic chemist does, in industry, like what is it actually that they're doing on the day-to-day. So a lot of organic chemists do something called organic synthesis, and that's basically the preparation of some, molecule that is of some interest to the company that, that organic chemist is working for. So maybe if you're working at Pfizer, a pharmaceutical company, and you're, preparing these various drugs to test against various diseases, we can't make most of those drug-like molecules in a single reaction, right? So it would be a series of reactions that allow us to take some commercially available starting material, that we're getting as a petroleum byproduct or something we can get from nature directly, and it's converting that molecule through a series of chemical reactions to our molecule of interest. Okay, so let me just give you that definition generally, and truth be told, I stole this definition directly from Wikipedia, but still I think it illustrates what we're going to be talking about. Okay, so we're talking about organic synthesis. Okay, and so organic synthesis we could describe as the systematic preparation of a compound from a readily available starting material by one or many steps. Okay, so I just want to break down that definition one more time, even though I kind of already talked about it. So it's the systematic preparation of a compound from a readily available starting material by one or many steps. Okay, so systematic preparation would mean, that would indicate that, the way in which we're doing this matters. Okay, and so we're making a compound of interest, so that would be like our drug-like molecule, from a readily available starting material, which would be our, molecule we can buy by the truckload from, some petroleum company or something. And then by the one or many steps, that's telling us the chemical reaction. So some syntheses may take 2 steps, some might take 20, and it really just depends on the molecule that we're making. Okay, and then back to the systematic preparation. So, the order in which those steps are carried out are important. Right, so the sequence of steps in our synthesis are important. Okay, so let's look at an example just to start talking about this. All right, so let's imagine that we took this alkene and we wanted to convert it to the corresponding alkyne. Okay, and this is actually something we already learned how to do, right? And this was, we called it alkene to alkyne synthesis. So I just want to point out how, we've kind of already introduced this topic, and then we'll look at a few other syntheses. Okay, so, there is no direct way to go from an alkene to an alkyne. And so what we learned is that we would have to first convert it to the dihalide. Okay, so the dibromide in this case. And that would be, oh, never mind, that's a meso product. And then from there, we can go ahead and do the dehydrohalogenation. So those conditions were NaNH2, 2 equivalents for an internal alkyne, and ammonia as the solvent. Okay, so that was a pretty straightforward synthesis. All right, so let's look at something, that maybe isn't as obvious or something we haven't specifically talked about yet. Okay, so what we want to do in this case, and I'm going to word this a little bit differently. Okay, so what we want to do is prepare this aldehyde from acetylene or ethine. Okay, so that aldehyde that we're making, that is our molecule of interest. That's the thing we want to make. And acetylene is the molecule we can buy through bucket load, buy by the bucket loads. And so there's a few strategies that we could employ or think about to complete the synthesis. All right, so one thing that I would always do is count the number of carbons in your starting material and your product and think about the functional groups that are present. Because, for this example, we only know of 2 ways to make aldehydes, and so it's gonna have to be one of those 2 ways because that's what we're limited to at this point. All right, and then in terms of carbon count, there's only one way we know how to make carbon-carbon bonds, and so if our carbon count increases, we know that we did some sort of acetylide substitution. Okay, so the product here, the one that we're going to make, has 6 carbons. Okay, so it's a 6-carbon chain, and we can see that functional group as an aldehyde. Okay, and then our starting material is only 2 carbons, and it's an alkyne. Okay, so as I mentioned, as we're increasing the carbon count going from 2 to 6, we must be doing acetylide substitution. Okay, so we can introduce something called the retrosynthesis. So the retrosynthesis is basically starting from the overall product and thinking, subsequently in the backwards direction to try to think about what each immediate reaction would give us in terms of products. So let me show you how that works. Okay, so the retrosynthesis. So this is a backwards approach. Okay, so we're basically going to start with our product, and we use these retro arrows. Okay, so these are retro arrows. Okay, so they point in the backwards direction. It basically says we're getting the aldehyde from whatever it's pointing to, so the starting material of that reaction. Okay, so I want to ask a question. So what are the 2 ways at this point that we know how to make aldehydes? Okay, so one of them is going to be basically the hydration, specifically anti-Markovnikov hydration of an alkyne. And then the second way, which is a little bit more tricky, would be ozonolysis of an alkene. Okay, so in this case, it would make sense to probably stick with hydration of an alkyne because alkyne is one of our starting materials, or is our starting material that we're using here. Okay, so let's think about then what alkyne starting material I would need to directly give me that product. Okay, so I have a 6-carbon chain. So if I had a terminal alkyne between carbon 1 and 2, that would be the alkyne I needed to perform that hydration. Okay, so I'll number my carbons so you can follow what I'm doing there. So basically the terminal alkyne between carbon 1 and 2, if I were to perform a hydration, specifically anti-Mark hydration with that diisoamyl borane, that would give me the aldehyde that is our overall product. Okay, so now we have to ask, how can I get to that 6-carbon alkyne? And so now we're just looking at acetylide substitution. So basically we can take our starting material and do acetylide substitution to add carbons 3, 4, 5, and 6. Okay, so we'll have carbons 1 and 2 as part of our starting material that was given, and then we can do acetylide substitution to get to the overall, that intermediate molecule that we see. Okay, so that would be like the backwards thinking. We're kind of thinking from the product that's given and working backwards till we can, arrive at the starting material that was given. Okay, and so then what would be the solution or the answer to this synthesis? Okay, or the answer. All right, so in this case then, this is where we're gonna go in the forward direction. We're gonna start with the starting materials that are given, and we're gonna give the reagents and conditions to complete the synthesis. Okay, so in step 1, we know we're doing acetylide substitution from our retrosynthesis. So I need NaNH2 and ammonia. That generates the acetylide anion, and then we can add our carbons. Okay, so in this case, we'll add carbons 3, 4, 5, and 6. That gets us to that intermediate that we had seen in our retrosynthesis. Okay, and now we need to go ahead and do our hydration, specifically our anti-Mark hydration. So this is where we need the diisoamyl borane, and then solvent, THF, and then the oxidation step, NaOH and H2O2. Okay, so there's an example of another synthesis. All right, so let's look at one last one, and then we'll go ahead and start chapter 8 after a quick break. All right, so our last synthesis here, let's go ahead and take this molecule. So we'll have this 6-carbon alkyne, And this is how I often will write synthesis problems out, is where we have this alkyne and through some number of steps. And the number of arrows here is not related to the number of steps. Okay, so that's really up to you to figure out. There might be multiple correct solutions to various synthesis problems. And so, at this point, I'm not going to grade for efficiency in any way, as long as you get to the product that was given, in a reasonable set of chemical steps, that would be a reasonable answer. Okay, so let's go ahead and make this molecule. So I want to go ahead and count my carbons just to think about what's happening here. Okay, so I have a 6-carbon chain in both, so I don't need to worry about any sort of carbon-carbon bond forming reaction, but we're thinking about how we're going to convert an alkyne to the corresponding dihalide. Okay, so one thing that you should think about is, well, what are the reactions that we know how to make a dihalide? Okay, so the reaction that we know of is the addition of X2 across an alkene. But what is the stereochemistry of that reaction? So remember that that is anti-addition. Notice how the way that the product is drawn here, the two halides are syn to one another. Okay, so in order to think about what alkene would be needed to give that corresponding dihalide, what I would first do is rotate around the carbon 3,4 bond to make those two halides anti to one another. Okay, so I'm going to go ahead and rotate around the carbon on the left. All right, and we can number our carbons. Okay, and I should note that this is going to be a racemic synthesis. All right, so now in this, this eclipsed conformation that we've come up with by bond rotation, notice how the two halides are now anti. Okay, so now I can go ahead and think about, what is the geometry of the alkene that is needed to get that? Okay, and so hopefully you recognize that, carbon 2 and carbon 5, they're on the same side of this carbon-carbon bond. All right, so that implies then that it's the Z or the cis alkene I need to go ahead and do this reaction. All right, so we can actually, I think, just jump into the forward direction of this synthesis. Okay, so we know we need the Z alkene. We just learned how to make that with H2 and Lindlar. Hope I'm still highlighting, I see. So let me draw that again. Okay, so we just learned this reaction with H2 and Lindlar. All right, and that gets us the Z alkene, okay? And it's the Z alkene that's required to give us the observed stereochemistry of the product. And this would form as a racemic mixture. Okay, so this shows us that, if there's some sort of stereochemical limitation to the reaction, we have ways to control the EZ selectivity of our alkene by going through the corresponding alkyne. Okay, so synthesis questions are really good ones to practice because they have you, practice the reactions as well as think about how to put them together in some sort of, logical way that allows you to affect the given synthesis that you want to do. So I definitely recommend doing, all the available synthesis problems in the workbook and the textbook just to really get a handle on these synthesis problems. And for exam purposes, 2, 3, 4 step synthesis would be reasonable. I would say not much longer than that. All right, I'm going to go ahead and stop this recording and I'll start a new recording as part 2, wherein we're going to go ahead and start chapter 8. Okay, so I'll see you guys all back here in a little bit.